I'm Gaylon Campbell. I'm a senior research scientist here at Meter Group. Today we'll be talking about how to measure and understand thermal properties of materials. So what are the thermal properties that we need to measure? The first two relate to how easily the heat flows through the medium. Thermal conductivity is a measure of the heat flow per unit area per unit temperature gradient. The larger the thermal conductivity, the more heat will flow for a given temperature difference. The thermal resistivity is the reciprocal of the conductivity, and it's used to describe insulation or heat flow in varied cables. Two more thermal properties are the specific heat. That's the amount of heat we can store in unit volume of a medium, and the thermal diffusivity. That's a measure of the rate at which a thermal disturbance will propagate in a medium. Now, in pure materials like aluminum or glass, the thermal properties are fixed or change very little except maybe with temperature. A lot of our discussion today, though, will be about porous materials like soil that have thermal properties that might change an order of magnitude or more, depending on the water content, the bulk density, and the temperature. In this graph, the lowest curve is for a cold soil with very little vapor flow occurring. The thermal conductivity there increases almost linearly with water content. Soils at higher temperature increase the thermal conductivity more rapidly as they start to wet up. We might wonder why that is. The extra conduction at high temperature is from the latent heat flow in the soil. The moist soil acts like a heat pipe. The water evaporates on the high temperature side of pores. It diffuses across the pore in the vapor phase, condenses on the cold side of the pore, and it transfers the water and the latent heat. When it condenses, then it returns in the liquid phase through the soil to evaporate again on the hot side of the pore and carry more heat. The 90-degree C temperature that's shown here, the heat pipe effect is even more effective in the vapor phase at transferring heat than the liquid water is. So the thermal conductivity up at high water content actually decreases as we increase the water content of the soil. Now, the volumetric specific heat for a porous material like soil also depends on the water content and the density. The change with water content is always linear, and it always has the same slope for every material versus volumetric water content. So that's pretty easy to model.